Hello, everybody. Thank you for joining me today. We're going to talk about how to supercharge query caching with AWS Database Services. My name is Steve Abraham. I'm a Principal Solutions Architect with AWS. And with that, let's go ahead and jump right in. First, I'd like to start off by talking about the general portfolio of AWS purpose-built database services that we have for a variety of different use cases in your particular applications. Starting on the top left, we're looking at relational databases, where we have Amazon Aurora, which is our OLTP relational database engine. We also, of course, support MySQL, Postgres, and other relational engines. Anything like Oracle, SQL Server, MariaDB, and those also come under Amazon RDS, which we will talk a little bit about RDS in a minute. The next row down, we're looking at non-relational databases, including DynamoDB, which we'll touch on a little bit later, and same with ElastiCache, and then for graph databases, we have Amazon Neptune. And then at the bottom, we have the AWS Database Migration Service, which of course is a very powerful tool to help you migrate into AWS and also to migrate between these different database engines. So let's talk about what the Amazon Relational Database RDS service is. If you have databases today, maybe you're running them on-premise, maybe you're running them in the cloud already, and you need to manage those databases, right? And there's a lot of work that goes into that is necessary for business continuity, things like backups, ensuring high availability, patching, things like that you need, but they don't really add any additional business value, right? And so in a standard organization, you might spend a considerable amount of resources just doing those things. What Amazon Relational Database Service does is it offloads some of what we call that undifferentiated heavy lifting, and we can take care of that for you. It's very easy to administer RDS. You can do so through the web console, through a command line interface, or even programmatically through APIs. It allows you to deploy and maintain the hardware, OS, and database software, and there's built-in monitoring that comes with it as well. So all of this can be achieved with a few clicks of the mouse or a few keystrokes in the command line. It's very performant and scalable. You can scale up or down, the amount of compute power and disk, and there's even a variety of different disk options to choose from, all to fit your specific workload. Availability and durability are a couple of the hallmarks of RDS, with the simple click of a checkbox indicating that you would like your RDS database to be what we call multi-AZ, and that means to span multiple availability zones. We automatically set that up for you so that you have a synchronous copy of your data in a different data center that runs on a separate set of electrical circuits and other things like that, so that it's highly redundant, right? And of course, secure and compliant, right? So with RDS, your data can be encrypted at rest and in transit, and we also are in compliance with a number of different programs that will meet your business's needs. Hundreds of thousands of customers use Amazon RDS. This is, of course, just a very small sampling, but some of these customers you may recognize, and all of these customers, they have a very high degree of, very, very high bar for, running their database systems, right? And so we need to make sure that we meet that bar, and that means that all of our customers, big and small, can all benefit from that very high bar that we need to set for running these relational databases in the Amazon RDS service. One of the things I wanted to talk about within RDS is Amazon Aurora. And while I could talk for the entire time about Amazon Aurora, I just want to give you a very quick view into what Aurora is and why it's different, right? If we look at this screen right here, what we see on the right is really a picture of what we call a region in AWS, a geographic region like Virginia, Oregon, London, Tokyo, Sydney, etc. And in there we have these different availability zones. And if you're looking at the availability zone 1, and if you imagine that is your master that is writing data to the database, and the other two and the other availability zones are readers, the thing that you'll notice there is there's a shared storage volume between them. And so that means that, your writer is writing to the same exact logical storage volume as what your readers read from. And this offers a significant advantage, and we'll get into that in a little bit when it comes to performance. I also want to point out too that shared storage volume is a logical construct. Physically speaking, there are storage nodes underneath it that are backed with SSDs. They're actually NVMe disks today that are directly attached. And depending on the size of your volume, you may have literally hundreds or thousands of these storage nodes. And each one of these storage nodes, we have 2 in each availability zone, right, for a total of 6 in what we call a segment, right? And so those segments can grow up to 10 gigabytes. And so that means that you'll never have more than a 10 gigabyte segment that maybe needs to be repaired at a given time. But in short, this allows us to scale massively for our throughput and in our performance. It allows us to automatically heal these nodes if one of them were to fail. And we also have continuous backup to Amazon S3, which has been built for 11 nines of durability. But the important takeaway here, I think, is that shared storage volume that the writer and all of the readers all have in common. So let's talk a little bit about caching now. Let's get, we've set the groundwork with, what the database offerings are at a high level within AWS. Let's talk about some of the native caching with the AWS relational databases. This right here, the buffer cache, is not something that's specific to AWS, but it is common across all of the relational engines that you would run in RDS. And if we're going to talk about caching, I think that it's important that we address this because this is your first layer of defense. This is the first entry point where caching is going to make a very big difference. So like I said, all of the engines that we're talking about, whether it's MySQL or Oracle or SQL Server, Postgres, they all store data in pages on the disk, right? And those pages vary in their size depending on the engine. But the thing they all share is that they're reading these pages off the disk. And those pages get read into memory, into a buffer cache or buffer pool. And when you're dealing with queries, whether they're selects or even if you're doing an insert, update, or delete, you have to retrieve those pages off of disk into memory, into that buffer cache. And so a very critical metric to look at here is the buffer cache hit ratio. And of course here we have an amazing buffer cache hit ratio in this picture where we're at 100%, and that would of course be ideal. But it's important that when we're looking at this that we want to emphasize that we have as high a buffer cache hit ratio as possible. And even though we're at 100% here, realistically for peak performance you want to be somewhere in the high 99s, so 99.5 or better. And you'll notice if that number starts to slip, if it starts to drop below that threshold, if you were to hold up next to this metric your read IOs, you would see those start to climb. And so as far as caching is concerned, caching those pages is critical. More cache hits equals less disk hits, and so you want to make sure that that is as high as possible. And how do you do that? One of the key ways you can do that is using the right-sized instance, making sure that you have enough memory allocated to the instance. Even if your CPU utilization is low, you could still benefit by having a higher buffer cache hit ratio. And so it's something that you want to do and sort of right-size your instances to make sure that you don't oversubscribe the amount of memory you have, but you have enough that you keep that buffer cache hit ratio high. Now, I talked about Aurora a minute ago, and Aurora is wire compatible with MySQL 5.6, 5.7, and also with Postgres, right? And so what that means is that from an application perspective, your application doesn't know the difference. But what we've done internally is we've made a number of key enhancements, and one of those we talked about the storage layer a few minutes ago, but another thing as it pertains to caches is we have taken in the MySQL instances the cache out of the main MySQL daemon and run it in its own process. And so what this means to you is that if the MySQL daemon crashes for whatever reason, and that happens from time to time, under normal circumstances with standard MySQL, since that buffer cache that is so important to the performance of your database is in that same process, it wipes it out. And so when it comes back up, you have to start reading pages off of the disk again, and so it's a slow startup. With Aurora's survivable caches, if the MySQL daemon were to crash and need to be restarted, that's okay, because the buffer cache is running in a separate process that does not crash along with that. And so when the MySQL daemon comes back up, it can resume processing with a warm buffer cache right out of the gate. So a significant improvement from a caching perspective. The next cache, when we're looking at the database engine itself, and this applies to Oracle, MySQL, and MariaDB, would be the query cache, right? So we've talked about the buffer cache caching pages, data pages off of the disk, but the query cache is actually caching your queries. So for example, if you executed a select query and it returned a given result set, that could be then put into the result set cache or the query cache, and the next time that query shows up, we don't even have to get all the way into the database engine in order to serve that query. Instead, it's essentially a key value lookup where the key is the query and the value are the results, and then we can just return that result set back. And so the metric you would look at to measure that would be the result set cache hit ratio. Now, I want to let you know that it's important that this is not always a good thing to use, right? There are certain workloads that will benefit from this tremendously, and for those, then I would recommend that you turn them on. If you have a very high result set cache hit ratio, then of course you want to take advantage of that because it will be lightning fast performance out of the database. However, if you find that you're not getting that many result set cache hits, then you're essentially wasting not only processing power by caching those result sets, but you're also wasting memory. And so that means you're taking it away from what could be used for the buffer cache. And so that can have an adverse impact on how your buffer cache is performing. So this is something that, it's powerful to use, but you want to make sure that you're looking at these metrics and making sure that it's useful for your particular workload. Again, with Aurora, we took what was already available in MySQL and then made a step forward with that. And so, running a Sysbench test versus standard MySQL based on the query cache size across the bottom, you can see that the Aurora Query Cache in most cases makes a substantial improvement over the standard MySQL query cache. So leveraging Aurora could give you some certain additional advantages as far as query caching. So let's talk about read replicas with these relational databases, right? So we've talked about, we have an instance, we've looked at the caching mechanisms that are built in to the engine on that instance, but we can also cache data on read replicas so that we can start serving reads out of those replicas, right? And so the read replicas, they're currently available in RDS for the MySQL, Postgres, MariaDB, and of course for the Aurora engines. And so these can be used to relieve pressure off of your master node and add additional read capacity. If you're able to split your read-write workload, then this will allow you to scale significantly. Another scenario where this can be used is that you can partition certain workloads to certain of these read replicas, and that will allow you to take advantage of caching a certain set of data on one reader and a different set of data on a different reader, even if it's from the same database. And so that can allow you to expand that caching capability by leveraging these read replicas. You can also bring data closer to your applications in different regions. And then in some cases, you can promote a read replica to a master in the event of a disaster. However, generally speaking, if you're looking at replicas within a single region, the multi-AZ option is usually the better choice because it's a synchronous replica. These are asynchronous replicas, and they will be kept up to date as best as possible, but there's no guarantee that they will be 100% synchronous. Now with Aurora, you remember earlier we were talking about how we have the shared storage volume, right? And one of the many advantages of this shared storage volume is that when the master writes its data to the shared storage volume, those readers can read it in a consistent fashion immediately. So if a record has been written to the table and committed, one of the readers, if it reads it from that shared storage volume, will read a transactionally consistent view of that data. And the other thing that's an advantage here too is that we don't have to copy any data between any of these nodes. None of the nodes in an Aurora cluster, not the master and none of the replicas, have any persistent data on the actual node themselves. Instead, they're all connecting to this shared distributed storage volume. So what this allows us to do is it allows us to have up to 15 read replicas, and any one of those can be promoted in a multi-AZ capacity. And we also typically see our replica lag at less than 20 milliseconds. 10 to 20 milliseconds is the general guideline on there. And that opens up even new opportunities for workloads because many other replication technologies can't do that. And then what we've added more recently is the ability to auto-scale these read replicas, right? And this can be based on either CPU consumption or the number of connections to your replicas. And so since we're not copying data between these nodes, the amount of time that it takes to bring a reader online is roughly equivalent to how long it takes to boot up an EC2 instance, because that is largely what we're doing. We're booting up an instance and then simply connecting to that shared storage volume. So it allows you to automatically scale those readers in a way that you wouldn't otherwise be able to do. And so what we did is we started out talking about the caching mechanisms that are local to the database and that some of them are specific to the database engine themselves. And then we drew the circle a little bit bigger and we looked at things like read replicas within a given region. But now there are a lot of applications that have reached a global scale. And when you reach that global scale, that means you have customers all over the world. And so it sometimes means that it's important to have caches of data that are close to those customers so that you can serve them more quickly. So how do we do this with AWS? We use this by doing cross-region read replicas. And so with RDS, we have cross-region replication available. It's supported for MySQL, MariaDB, Postgres, and Aurora MySQL. This can allow you to, create readers in different regions so that it's essentially a cache of that database in a different region. So for regional customers in that area, they don't have to go all the way, to the other side of the world to retrieve their read data. They're able to read it locally, and that can improve performance substantially. Of course, you can also leverage cross-region replication for disaster recovery. And another common use case is migrating to a new region. Maybe you launch a business in one region and then it takes off and you find out there's another region where you have a high concentration of customers. And so you decide for whatever reason you want to move your operations there. This is a great way to initialize that move to a new region. With Aurora, we still do offer we're using bin log replication under the covers today to replicate between regions, but coming very soon, we will also have what we call Aurora Global Replication. And what this is that when the writer in an Aurora cluster performs a write, what happens is we generate a redo log. And we write that redo log to the storage node. We actually write it to 6 storage nodes, 2 in each of 3 availability zones in a region. And then we wait for a 4 out of 6 write quorum. Well, when we use Aurora Global Replication, that all remains the same. It's exactly the same. The main difference is that there is now that record is also going to be written out to a replication server. It's called a replication server in this diagram, but don't think of it as a single instance. Think of it more as an endpoint that is highly available and highly durable. And so that replication server is going to receive that same redo log record, and it will separately from the storage nodes that it's writing to in the primary region, it will copy those across the wire to a replication agent, which again is a highly available, highly durable endpoint in a different region. And that replication agent will then take that redo log and distribute it across the storage nodes in its own region. And so one of the advantages here architecturally is that with any other replication technology, you would need to have a replica, a compute instance that is online and running in that second region. With Aurora Global Replication, that's optional because the replay of that data, the actual application of that data with traditional replication technologies requires that compute resource to, say, replay a bin log, for example, in that other region. With Aurora, that's happening from that replication agent. And so it's possible to have a headless Aurora cluster in the other region as part of a pilot-light architecture, where in the event of disaster recovery, you could spin up that compute node or whatever compute power you need on there and be online and running in a matter of minutes. Otherwise, this is a much lower latency option with a lot less overhead than traditional bin log replication, because again, we're not counting on the compute instances to do any of either the generation of the bin logs or the replaying of the bin logs. That is, that we're now instead just shipping redo logs storage layer to storage layer. So let's shift gears a little bit and move from relational databases into NoSQL databases and how we can achieve caching with AWS NoSQL databases. Amazon DynamoDB is the primary NoSQL database within the AWS portfolio, right? It's very fast and flexible, and it can scale to virtually any scale that you might need. It supports, it's a key value NoSQL database, and it supports document and wide column structures, highly scalable, and I mean very highly scalable, again, like I said, to virtually any capacity that you could foresee. Fast, consistent performance. It's fully managed, just like RDS. So it's as easy as creating, provisioning a table, defining that table, and then you're able in defining the capacity, and you're ready to go. Very simple, very easy to maintain. And then, of course, business critical reliability. The data is replicated across multiple AZs, and you can access it with regionally available APIs. So it's very reliable, very durable, right? And so if you've decided that you need a key value store or document store, or you're looking for your NoSQL database and you choose DynamoDB, like this sampling of hundreds of thousands of other customers that use DynamoDB, some of them you likely recognize, then the DynamoDB Accelerator, or what we call it as DAX, would be the caching mechanism that you would use here. Now, DynamoDB on its own is incredibly fast, incredibly performant. But with DAX, we offer a fully managed and highly available caching solution in between the application and DynamoDB itself. DAX is fully scalable, can scale out to handle millions of reads. One of the things that I think is particularly powerful is that it's compatible with the DynamoDB API. So that means that you don't have to rewrite your application in order to leverage DAX. It will just work. It's a write-through query. That's another thing that I think is very powerful too. So it handles caching on writes. It's flexible. You can configure it for one or multiple tables. It's fully integrated AWS service, so that means it works with CloudWatch, tagging for DynamoDB. You can access it through the AWS console. And of course, like our other data services, is very secure. You can access it from within an Amazon VPC, supports encryption at rest, AWS Identity and Authentication Management, and also AWS CloudTrail. So some of the key benefits here is the read performance. Like I said, it moves from milliseconds down to microsecond response times, even while maintaining scale of millions of reads per second from a single DAX cluster, right? It's very easy to use. Like I said, it's fully managed, and it's fully compatible with the DynamoDB. It is compatible with the DynamoDB API, so it does not require any application rewrites in order to use it. And of course, you can lower your costs here too. So if you're familiar with DynamoDB, you know that when you create a table, you allocate read capacity units and write capacity units. And then your fee is associated with how many of those you allocate. So by using DAX, if you have a very read-intensive application, it may be possible for you to lower the read capacity units on your table or tables because a lot of that data ends up being cached at the DAX layer. So traditional caches, and and there's nothing wrong with this. I mean, we certainly have seen lots of customers do this, and they do this with all kinds of different technologies. But traditionally, you might see a side cache, right? Where you're going to first look in the cache, and if it's not in the cache, then you're going to go to the source of truth, in this case DynamoDB. When you retrieve it, then you need to update the cache. So there's a lot of communication back and forth, and it can also complicate application development to some degree. Now, compare that to what it looks like with DAX, where it's an inline cache. So your reads and writes go directly through the DAX endpoint. And then DAX will take on that undifferentiated heavy lifting of managing the cache. You write directly through the cache, and then you read from the cache. And if it's not in the cache, DAX will get it for you and populate it into the cache for you. So it greatly simplifies application development and cache management. And so when you combine these together, you end up with a very fast, very responsive DynamoDB. You're going to want to use DAX if you need extremely low read latency. So we're talking sub-millisecond response times, right? If you need to scale your reads, we're looking at millions of reads per second from a single DAX cluster. Again, high volume, right? High read volume and very low latency is really what you're looking at, and possibly is at a lower cost as well, depending on what your workload looks like. Here's an example. On the left, you can see a handful of calls that are not too bad. I mean, we're still hitting 4 or 5 milliseconds, which for most applications is perfectly acceptable. It's a great, latency time, right? But if you look with DAX on the right, it's significantly less, right? I mean, we are sub-millisecond is what we're looking at for these calls with DAX. So very, very low latency, high throughput. DynamoDB with DAX is also highly available. We leverage the multi-availability zone paradigm where you can have DAX clusters in different AZs that are reading and writing from DynamoDB. And then, of course, for scalability, you can either scale up your DAX cluster up to an R4 16XL, which will give you 488 gigabytes of memory, or you can scale out for read volume and have up to 10 read replicas. Let's look into application caching. And so what do I mean by application caching? I mean, we've talked about, the specific caches they're specific to relational databases and to RDS, as well as the ones that are specific to DynamoDB. But sometimes you need to cache other data, or maybe even with those pieces of functionality in place, you may still want to augment some other caching mechanism within your application. And so that's what we're looking at here. And so the tool that we see in the AWS portfolio for that would be ElastiCache. And so ElastiCache, very similar to RDS, right, it's a fully managed, either Redis or Memcached compatible low latency in-memory data store. And what I mean by it being similar to RDS is that, we're just like in RDS, we run, MySQL and Postgres, for example. In ElastiCache, we run Redis or Memcached, which are both very popular engines that are available, are in wide use, around the world today with applications. So if you have applications that use those today, then we take on that undifferentiated heavy lifting for you so that you don't need to focus on managing those clusters. You can just use those automatically with your application without any application rewrites. We also make it a lot easier to scale those, and that also takes on a lot of that undifferentiated heavy lifting as well. Just like the other services we were talking about, there are thousands of customers that use ElastiCache. Again, maybe you recognize some of these, but a lot of customers love ElastiCache. Query caching with ElastiCache and RDS. Remember I was saying, we might use ElastiCache to augment, RDS or, some other, data store. It looks a lot like this, right? You're doing reads and writes, to the RDS, your database, whether you're running MySQL, SQL Server, Oracle, Postgres, whatever it is. And then when you get values back, you can cache those. You can write them into the ElastiCache for Redis or for Memcached, right? You can also use other data sources like MongoDB, Cassandra, maybe even S3. It depends on what it is that you're caching, and you can store all of this in memory in ElastiCache, and so that can give you incredibly low latency response times for some of these other data stores that are, maybe not as quick as, that sub, millisecond type response time that you can get out of using ElastiCache. Now, of the engines to choose from, there are two. The first of which would be Redis. It's very fast, less than 1 millisecond latency for most commands, right? And so that's a lot faster than you can expect out of a lot of other data stores. And so it makes a lot of sense to cache your data in something like Redis, where you can offload that workload from your other data store and also provide incredibly fast access for your customers. It's open source, it's simple, we can make it highly available, or rather you can by selecting multi-AZ configuration when you're deploying your Redis cluster. It supports atomic operations. It's an in-memory key value store. It is actually the #1 key value data store. Is what we can see online today. It's very powerful, about 200 commands, Lua scripting, geospatial. Also, if you're looking for pub sub, this is another option that's available with Redis. And then there are a variety of different data structures. The other engine that we have available is Memcached. Memcached is also incredibly fast, also open source, but there's no persistence. It's very established. It's been around for a long time. It's easy to scale. It has a slab allocator. It supports strings and objects. It's multi-threaded, and I think that's one of the key advantages with Memcached. And it also is an in-memory key value data store. From a high availability and reliability standpoint, when we're looking at Redis, for example, we can leverage read replicas for read availability. A lot like what we would do with DAX, where we can have replicas there to scale reads, or with RDS, where we would have read replicas. So we can scale those reads. Those are, essentially caches of the same data that you're caching. Multi-AZ with auto failover. So again, for high availability, you can configure your ElastiCache cluster so that in the event of a failure, we will automatically fail over into a different availability zone and continue to run your cluster and keep it online. We can repair failed nodes automatically as well. Redis cluster sharding allows for faster failover and availability due to partitioning. It's easy to scale with the Redis cluster mode as well. You can scale memory and compute up to 6.1 terabytes of in-memory data. So we're talking about 6 terabytes of data that is cached with a sub-millisecond response time to serve that data up, right? A cluster consists of 1 to 15 shards, and each shard will have a primary node and up to 5 replica nodes across multiple AZs for read scaling. So you can see that we can scale tremendously with Redis on ElastiCache. And then you can, of course, increase your writes by adding additional shards. If you're trying to decide between which engine should you leverage, this chart right here will provide a quick breakdown for you. You can see all the features along the left and then how they stack up. Like I was saying, Memcached, the area where it really shines is the multi-threaded architecture. You can take full advantage of all CPU cores, but you can also see that Redis has a significant number of other features that Memcached does not currently. But it really breaks down to these key features right here seem to be the key differentiators, right? And so if your application needs these features, you might want to take a look at Redis. Otherwise, you might want to take a look at Memcached. It's completely up to the application's need. So let's take a look at some example architectures. What we're looking at right here is we're looking at leveraging something called pgpool with ElastiCache, right? And so with this, you can see that in the middle we have an application. And that application, in this case, is querying from Amazon Redshift, which is our data warehouse platform, right? But you could replace that Amazon Redshift with an RDS database. You could replace it with a MongoDB database. You could replace it with well, not MongoDB, but you could replace it with any other, database that's supported by pgpool, and then your application talks directly through pgpool, and then it will hit, ElastiCache if the values are stored there, and if not, it will hit the data source, in this case, Amazon Redshift. And for those of you that are familiar with data warehousing and with Redshift in particular, Redshift and other data warehouses, for the most part, are not designed for high volume throughput, right? And so if you have an application that needs to query a data warehouse, but you want to be able to enable more users to access that data warehouse, then using an architecture like this where you have pgpool in front of it that will cache those results in ElastiCache, especially since you know that the values in a data warehouse change very slowly, it's likely that you're going to get a very high cache hit ratio when you're hitting ElastiCache, and it will offload a significant amount of work from your data warehouse, in this case, Redshift. Now, here's another architecture we can look at, which is leveraging the API gateway with Lambda and DAX. So let's say that you're building a serverless application, right? Your application makes an API call through the API gateway. That API gateway call is backed by a Lambda function, for both a post and get, right? And so then those Lambda functions, they talk directly to the DAX cluster. And that DAX cluster will manage the caching, and it will handle both the reads and writes into that DynamoDB table. And so this gives you that high durability of having the data actually stored in DynamoDB, but it offloads a lot of those reads from DynamoDB, which can then lower your cost and also increase the read throughput and lower the latency by serving those hits up out of memory in the DAX cluster back to your Lambda application directly. Here's a quick look at one of our customers that uses RDS and ElastiCache. Grab is a popular taxi hailing app in Southeast Asia, and their required API latency is less than 40 milliseconds. So that 40 milliseconds is going to factor in a number of different things. It's not just a query, it's API latency, right? So everything in the API has to be able to respond in less than that 40 milliseconds. Initially, they were running Redis on EC2, but found that there was, like I said earlier, a lot of undifferentiated heavy lifting. They spent a lot of time managing the Redis cluster rather than, being able to focus on the application and the thing that really differentiates them as a business. And so they decided to move from Redis on EC2 into ElastiCache so that they could scale their employees as well as scale their Redis infrastructure. And so today, using RDS and ElastiCache, it allows them to rapidly scale and lower their operational overhead, because with both their caching and their relational database management, that has been offloaded onto AWS, and so they don't really need to worry about that or manage that. I'd like to offer a few links here. If you'd like to learn more, you can learn about the AWS free tier for databases, the AWS Database Services info. You can follow these 2 links. And other than that, I would like to thank you for your time today.